Welcome back to this module on exploiting DLP using SIMD instructions. In this lesson, I will present different ways of supporting control flow in SIMD instruction set extensions. Data parallel loops. If the same instruction, the same operation needs to be performed on all data elements, is problematic if the loop contains if-then-else statements, if the loop contains control flow. Here's a very simple example that implements the absolute value of image pixels. If the image value is less than 0, then the new image will become minus image I, else the new image I stays image I. How do we deal with this? There are two common solutions. Either we make element masks or bit masks, and both have their advantages and drawbacks. Element masks, that means that we support comparison instructions, and the outcome of a comparison is an element mask. That means we have a factor of different elements, and each element either contains all ones or all zeros. These masks, these element masks, are then used together with the conventional logical operations, bitwise AND, bitwise OR, bitwise NAND, to achieve the desired conditional assignment. For example, MMX like P compare equal then, element is the suffix of the instruction, and P compare greater than, the element size is the suffix of the instruction, generates these element sizes, element masks. And then we can use bitwise operations to select the right operands for an instruction. Another possibility is to produce comparisons, produce bit factors, meaning a single bit for each comparison, and these bits are used together with partial stores to generate the desired result in memory. For example, suppose we only want to store the word 73 here if it is larger than a corresponding element of this factor here. Then we see that the less than comparison yields a bit 1, true, corresponding to true, false, corresponding to 0, again false, again false. So in the register 1, a bit factor consisting of all zeros except one bit corresponding to the first less than comparison is produced. Then we have a partial store that writes to memory the elements of factor V1 provided the corresponding bit in R1 is set. That means in this example we only replace the value of 51 in memory by the value of 73. Again, quite complicated solution, but control flow and data level parallelism is not an easy topic. To summarize, we've seen special purpose instructions supported by some SIMD extensions, in particular the sum of absolute differences, but packed half or packed average is another example to avoid data promotion. Sometimes we require unpacking, data promotion, or packing, data demotion between different data types in order to calculate with higher precision for intermediate results. Some SIMD ISAs allow unaligned memory accesses, but then they are slow. Other SIMD instructions disallow unaligned memory accesses altogether. The most powerful data permutation operation is the full permutation instruction operation supported, for example, by Ultivac.
but in most cases we don't need the full power of a full permutation, and the most common data permutation operations can be implemented using simpler data reordering operations. And the final thing to take home is that branches and control flow in data parallel loops are extremely challenging, and no real good solution that works in all cases has been found.
This concludes this lesson. Thanks for watching. In the next lesson, we will look at how the SIMD instructions can be employed using Intel's streaming SIMD extensions as an example. Stay tuned.